implement these actions. The expressions and statements are very straightforward. They're very regular. So I'm sure even if you don't have a compiler background, writing those actions is very straightforward. But for most of you, you'll be using the SEMA action module. So it comes with an action module that most people are going to be using. And as I said, it does a semantic analysis and type checking. And if it's not well formed, an abstract, if it is well formed, an abstract syntax tree pops out the other end. If there are problems, then you don't get an abstract syntax tree. So the design point is when you have an AST, you know that it's well formed, right? The other tools in the chain do not have to be paranoid about the state of the AST. Okay. There's one minor exception. When we're parsing declarations, declarations are so coarse-grained that there is actually a bit in the declaration to say whether there was an error in it. But in general, you don't have to worry about that. Yeah.
Do you have to build up the data structure in your SEMA actions? I mean, isn't it typical to build an AST and then do analysis on that? You know, correcting or...
That's where we're different. No, we do the analysis, and then what pops out is a less abstract syntax tree. Right. Oh, okay. Take the questions at the end. Okay.
Repeat the question.
Oh, repeat the question.
You repeat the question.
Well, can we do it later? Let's do it later.
Okay.
So here's an example of one of the specific delegate hooks. I'm starting simple. So act on numeric constant. If you have a C numeric constant, the token will be passed in. SEMA will do the checking. And then what pops out is an integer literal or a floating literal. So the semantic analysis is not done in the lexer to determine whether it's an integer or float. It's done in SEMA. And this is because in C, you could have a constant with L's and U's and dots and all kinds of stuff. And that analysis is done by the semantic analyzer. The constant ultimately has to have a type, and that type is determined by SEMA. Right? The next action I'll show here is a little bit more complicated. If you have an identifier, right? You have a variable, X. It's passed in a scope object, a location, the actual identifier, and then this funny argument at the end, which is because we're dealing with C, has trailing paren. So in that case, the semantic analyzer, if it's looking at an identifier and that identifier is, let's say, a function call but doesn't have a prototype, it needs to know whether there's a paren trailing it. And here we have a decal ref expert, which is the common object that pops out, but if you have an instance variable reference or a C++ member reference, that's what pops out. And lastly, we have an expression here. Let's say you want to act on a call, a function call. These expert type defs are just there for documentation. The SEMA actions take untyped objects, right? Because we want the actions interface is generic enough that we want you to be able to supply your own objects. Talk about that in a minute. But they're there for documentation. So here you have the function that's called, which is an expression, the location of the left paren, the arguments, the number of arguments, and the locations of the commas, and then the locations of the right paren. Okay? That's how it works. So now let's, just to emphasize the design point, is we have this thing called Clang-parse-no-op. And what this does is just implement 6 act-on methods to do type recognition. Type defs, classes, and Objective-C that you need to parse. And this doesn't produce any diagnostics, and it doesn't produce any objects, but it does parse the entire program. This allows us to do timing analysis. Okay? It also promotes this clear separation between the parser and the semantic analyzer. So for example, a lot of our tools are going to be based on action modules. Okay? let's say one day there was some compiler that we absolutely loved, and we were sick and tired of maintaining the hand-built recursive descent parser. It turns out that as long as that new parser implements the set of actions, we can do a brain transplant and disrupt none of the code that sits on top of it, right? So because of this clear separation, it allows the parser to be reused and replaced really easily. And again, because we spend only 10% of time in parsing, this separation gives us a lot of bang for the buck, because it's really not a performance problem. AST requirements, we want to support multiple diverse clients. You know, modeling a program for diverse clients is actually a tricky thing. It requires you develop those clients hand in glove with the data structures. So we are developing many different applications to basically validate what we've done with the ASTs. So for example, one of the modules I wrote over the past year was a fancy rewriter that refactors code from ObjC to C code. Okay? And to refactor that means you have to get the line numbers correct. Okay? And when I was doing this, just as sort of a fun project, it showed bugs in the source location stuff. Some objects didn't have enough source location. Sometimes the source locations weren't correct. So again, as we develop these libraries, we need to have little projects and exercises that validate what it is we're doing. We want them to be high performance. It turns out that there's only a small number of objects that you really need to care about performance on, identifiers and types in particular. So we unique them. And qual type is a smart pointer class for storing, you know, the type qualifiers and selectors. So these guys, we don't have to go into detail, but if you look at them, they've been highly optimized, yet they still have a nice interface. Okay?
Steve, you have about 10 minutes left.
10 minutes? Okay. Thanks, Ted. The integer literal class, here's just to show you a simple class. It leverages the arbitrary precision integer in LLVM. There's a constructor, there's getters, very straightforward. It does an assert in the constructor to make sure the type is correct. And here are iterators, serialization, and dynamic type support. So the serialization are the hooks that write the object to disk and read it. Iterators should be obvious. I'll give you an example in a minute. And the dynamic type support, these are hooks that